Right. Hello again, everyone. This is lecture 16 in high-dimensional probability. And we keep discussing applications for about 4, maybe 5 lectures. This time we will get into the area, a big area that's called combinatorial optimization. Which basically studies the problems like, well, how do we make a best decision out of finitely many decisions available? In the usual optimization problems, we have infinitely many of them, such as we maximize the return, for example, maximize the profit in some parameter, and we differentiate and something like that. We get maybe the derivative or the gradient or something like this. But here, in the area of combinatorial optimization, it's discrete. So it's much, much harder to do optimization. There are easy and there are hard problems in combinatorial optimization. And we will start with the, let's say, with the easiest one. So problem, here's one of the kind of easiest problems. Let's say we're given numbers, a1 through an, real numbers. And we would like to find the maximum maximum of these numbers with sign, the sum of these numbers with signs. So xi's are allowed to be plus or minus 1 signs. So we just, here's the numbers, a1, a2, a3, let's say a4. And I would like to find the signs like this, so that the sum is the biggest. So I either add numbers or I subtract them. So if this problem is easy, actually.
This is a sign of the number?
Exactly, yeah, just a sign. Yeah, just take the signs of the numbers, precisely. So if we didn't know anything about mathematics, right, just thinking of as a computer, we would say, okay, just do the exhaustive search, put all combinations of signs and then choose the best. And there are 2 to the n combinations of signs. Right? So if we did not think about this problem, we could have run this for 2 to the n time, which is too long, but we know how to solve this problem. Exactly, this problem is solved just by choosing the signs, xi's, the numbers xi to correspond to the signs of this. So if the number is positive, basically the number is positive, you need to add it. If the number is negative, you need to subtract it. So that either way you increase the sum. That's the best possible solution here. Here we go. This is an exact and direct solution to this problem. Okay, so far so good. Okay, that was kind of base level. Okay, next one step up. Now let's say we are given a matrix of numbers, an array of numbers, aij, from 1 to n. So we have a matrix, and we would like to find same thing, I and j, now go from 1 to n, aij, and we also allowed to choose the signs in this way, xi and yj, they are the signs, plus or minus 1, just like that. This is problem 1, let's say. If we allowed here to take xij, if we allowed to choose individual signs for each entry, then that would be the same problem, right? We just choose the signs corresponding to the entries. So that would be an easy problem, but we are not allowed to do that here. Instead, we're building a quadratic form the sum of xi yj is bilinear form with integer constraints. In fact, Boolean constraints, 0 or 1 or -1 and 1. And that problem is suddenly not only it is harder, but it is actually NP hard, which in theoretical computer science stands for a class of problems for which it is believed that that there is no easy way out, no polynomial algorithm that would polynomial time algorithm that would solve it. It is an NP hard problem. It is an integer problem where the constraints xi's and yj's are, well, not only integers, we restricted them to plus or minus 1. And it is also quadratic, or actually bilinear. Both of which are a problem. Quadratic problems could be hard, integer problems could be hard, and this is both. Is it clear? Okay. Yeah. Okay. So what happens in the rest of this class? We'll take this problem. And I will explain how this arises in different problems, in different situations in the data science. Specifically, this problem or its variants, this Boolean optimization problem, and then we'll try to solve it in a different way, in an approximate way. So related problems. How does this problem arise? So first of all, if we let x be the same as y, so if we want to choose the same signs, so xi's are plus or minus 1, and then we have not a bilinear form, but really a quadratic form, xi, xj. This is still NP hard. It doesn't simplify anything. So it's maximized the quadratic form over Boolean cube. It is still a hard problem. And this was first proposed and still is very actively used as so-called Ising model. Ising model in physics. Specifically, it's easiest to explain how it relates to magnetism. So it was Ising model that first attempted to explain the magnetism. Ising was a German or German, I think, mathematician. So in the United States, it's pronounced Ising, but it should be pronounced Ising. So here's how magnetism can be explained. We have atoms, maybe in crystalline structure, maybe like a ferromagnetic structure, something like that. So we have atoms, and the atoms interact with each other. Each atom has a spin. Actually, it's neutrons and protons have the spin, but collectively, let's say the total spin can be either positive or negative. So it derives the spin from the nucleus. So each atom has a spin, either positive or negative. Actually, it's more like a physics notation, but let me just say +1, maybe -1, +1, +1, -1. So I'm looking at the spins now. The atoms interact and derive their energy from the interaction between the atoms. If the spins are the same, let's say, they're plus and plus, the energy, I think, increases. If the spins are different, the energy also increases, the opposite. -1, the energy also increases. If the spins are opposite, the energy decreases, something like that. So the total Hamiltonian, the total energy is just the quadratic form. Let me write this down. So again, the Ising model of magnetism, Xi is the state of atom I. In this case, the spin is the state, so ±1. Aij is the strength of interaction. So derivative of energy, interaction between atoms I and J. And H of X, if we sum all these interactions over all atoms, Aij, Xi, Xj, this becomes what physicists call Hamiltonian, which you may basically the energy, the free energy of the system. For example, if Aij is greater than 0, this corresponds to ferromagnetic state, ferromagnetic materials, where the atoms want to have the same spin that increases. So here we go. So that's Hamiltonian of the ferromagnetic system, or in general disordered system. And the problem here, the maximization problem, is to find the maximal possible energy of the system. What configurations of spins gives maximal energy? Good. Okay, that's one. That's physics. Let's see. Another related problem. This one is closer to data science. It's about clustering. Clustering of points. Let's say we have points now, not atoms, but just data. Data points like this. Okay, maybe it's genome. Each point is one person, and the vector of these points is genome, for example. So we put it in high dimensional space. There are, let's say, n patients and the number of genes we collect is d for each patient, and we would like to classify we'd like to see if it clusters, if there are two populations really here. Well, maybe these populations are, I don't know, cancer and non-cancer patients. Can we separate them? And so we put this in high dimensions. This is a picture. And how do we actually find these clusters? There are methods. And one of the brilliant mathematical ways to do this is to set up a quadratic form like this. And here's how. So we look at now Aij will be the distances between the points. Pairwise distance, just like in Johnson-Lindström's lemma. Distances, okay. Let me think. And now what we want to have when we cluster the points. Well, first of all, what does a cluster even mean mathematically? Right? How do we? So we know all these distances. We just don't know which point belongs to which clusters, but we know all these pairwise distances. I don't include all of them, but really we know all of them. If we expect clusters to form, we might think of them as follows. The points within each cluster will be closer than the points across the clusters. right? So the clusters are something tight. So the distances within distances, interior distances in each cluster must be collectively smaller than the distances separating the clusters. So for example, this distance is smaller than this distance, should be smaller generally. There may be outliers, but still. Okay, so how do you set it up? We can just set it up as a by adding the points, the distances in one cluster, adding the distances in another cluster, and subtracting the distances between the cluster, and then minimizing that. So we would like to have the distances smallest within clusters, largest across clusters. So if we set a functional that adds the distances within, subtracts the distance without, and then minimizes it, that will win. That's what we want. We want to have it the smallest. So we want the sum of distances in cluster 1 plus the sum of distances in cluster 2 minus, let me make a leap of faith here, minus 2 sum of the distances between. The points between the clusters. Okay, so how do you set up this potential? How do you set up this function? We can say something like this: assign +1s to points in each cluster. Let me think. Assign +1s to points in one cluster, assign -1s to points in the other cluster, like spins. And then do the following. So equals, and then just do the quadratic form. Sum of aij, xi, xj. So what happens here, if we are in cluster 1, let's just think together. So if we are in cluster 1, then xi, xj will be positive, right? So we're adding the distances. If we're in cluster 2, the pairwise distances are the signs are both negative cancels, and we're again adding this aj's. So we add distances here, add distances here. And if we are across the clusters, the signs are opposite, plus minus 1. And so we'll be subtracting aj's. Maybe the metrics will help here. So this is a matrix of distances. This is aij's, and this is x, let's say xi and xj here. Some of these distances, some of the signs are +1, and some of them are -1. So we'll break it into a structure like this. Sign here will be plus, plus, minus, minus. So we maximize, we minimize, sorry, we need to minimize now. Minimize, i's and plus or -1. Good. Yeah, so we're adding distance in cluster 1, in cluster 2, and then subtracting twice the distance between the clusters. Minimization will lead to the clustering.
So I ask the question, so this specifically for 2 clusters, right? Because in terms of distances, it generalizes easily to multiple clusters. But
yeah, exactly. Yeah. This is specifically for 2 clusters. This particular form works for 2 clusters, and we will actually, maybe I'll comment on how we make it work for many clusters. It's in fact, let me actually give you a reference. It's Fries and Jerem proposed this method in 1997 for many clusters. So basically, just to give you a hint, if xi's are just numbers, the signs plus or -1, plus or minus 1, that will encode 2 clusters. If we make xi's a little bit higher dimensional, let's say they're in 3-dimensional space, so that they are not signs anymore, but we have 3 points on the sphere, on the circle. Just take the circle and put equidistant points there. This is a kind of a metaphorical signs in 2 dimensions. Now we have 3, we can work with 3 clusters. We can adjust this program to work with 3 clusters as well, and 4 clusters, and so on and so forth. So that's possible. Yeah, it's a very good question. Good. Any other questions? Okay, so this is it's still NP-hard, and I didn't say that we can solve it. It's clustering is actually NP-hard. So this is hard. The program itself, the problem itself, like this is equivalent. The minimum and maximum are the same, actually, right? I just want to make sure that you understand that this is the same as maximum of minus aij xij. So minimum and maximum are the same. Just you flip the signs of the entries and you can minimize instead of maximize. So no big deal. Also, this clustering approach works in arbitrary metric space, not just Euclidean metric. What I'm saying is basically we don't have to have the Euclidean distance. Any kind of similarity or dissimilarity metric would do. If you have any other way of comparing the data, not Euclidean metric, fine, it works, because it only depends on the distances. But good. Number 4. Next problem that is also equivalent to all this is maximum cut of a graph. Here, the problem is kind of opposite. If in clustering, the problem is to separate the clusters, so to make as little as possible connections, like you would cut the graph so that we cut through as few as possible connections. In max cut, the problem is opposite. We want to cut through as many as possible. We want to separate the graph as if it was a bipartite graph. So it has 2 parts and a lot of connections between and very few within. So it's kind of an opposite problem. And it's one of the central problems in computer science. So here's my picture of the graph, I guess. We have vertices denoted by V, the set of vertices, the edges, connections between them, denoted by E. And we would like to separate the vertices, the set of vertices, into 2 classes to maximize the number of connections across, like this. We would like to take scissor and cut through as many edges as possible. So max cut of the graph is formally defined by taking the number of edges. You're looking at edges between V1 and V2. Take the number of them and maximize it over all partitions of the set of vertices into 2 disjoint sets, V1 and V2. And this union, the quadratic union, just indicates that it is a partition. The sets don't overlap. Is my notation okay, clear? Yeah. Perfect. Let's write it as a quadratic form. Okay. So without loss of generality, WL of G, without loss of generality, we can identify the set of vertices with numbers from 1 to n. That will help us set up metrics. So the vertices are just labeled 1 through n. And a very, very useful and important object in the graph theory is the adjacency metrics. So instead of looking at the graph, which is mess, like edges go everywhere, how do you look at the little web? You look at the metrics that completely encodes the edges. A matrix, vertices as columns, vertices as rows, and the matrix is 0, 1. 0 if the two vertices are not connected, 1 if the two vertices are connected. So it's a matrix full of 0 and 1 and completely encodes the graph. So that's how you put the graph in a computer, for example. So A E will be the adjacency. Adjacency matrix. What is it in Ukrainian? Do you know? Adjacency.
Матриця суміжності чи щось таке.
Yeah. Thank you. Суміжності. Матриця суміжності. Perfect. Thank you. So Aij, it's 1 or 0, depending on whether there is an edge, a connection between the vertices or not. Okay. That's that. Okay, how do we compute now the number of edges between the two sets of vertices? If this is like V1, this is V2, and I'm looking at the matrix, I would like to include this and only this in the count, right? I would like to, if this is my A, I would like to sum the entries just there. That will be the number of edges that connect V1 to V2. Okay, so I would like to set up this as 0, this is 1, this 0, and 0. So how do we do that? Let's think. So E of the number of edges between V1 and V2, I can write it as the sum, hopefully. Aij xi, yj, I guess, where xi is 1 if the vertex I is in the set and 0 else otherwise, and yj is obviously for the other set. But that's bilinear form. Not quite. I just want to get rid of yj's here.
But it's symmetric, so can we just count twice those quadrants and divide by 2?
We can, but still bilinear. You'll still get yj's, right? This way. Yeah, we'll do like xi yj plus yj xi or yi xj.
Yeah.
Yeah. I just want to have like xi xj, and that's or something like that. And get totally rid of yj's. But that's actually simple. You see, xi's and xi and yi, they depend on each other. They actually determine each other. Just think, xi, what is xi? It determines if the vertex is in the first set. Well, if it is in the first set, then it is not in the second set, and the other way around. That's partition. Yeah, you got that. So yj is actually 1 minus xj. That's because these sets are partition. If I is in V1, then I is not in V2. And if I is in V2, then it's not in V1. So it's 1 minus xj. And so let me just correct this. Xi times 1 minus xj. Actually, sorry, let's not correct what we have, just rewrite this here. So the max cut of the graph, the maximum cut, asks us to maximize the quadratic form, ij from 1 to n, aij, xi, 1 minus xj, still a quadratic form. Yeah, good. And still NP hard. But then we have these problems coming over and over. That's various forms of this problem. Maximize the quadratic form over a discrete set, in this form over Boolean cube, either by linear form or quadratic form, or some version of the quadratic form like this. But either way they come. That's the whole class of problems that keep showing up in the theoretical computer science and data science as well. And so the question is, how do we solve that? If this shouldn't be hard, maybe we can approximate and maybe we can do something. Before we go further, any questions on the setup of these problems? Good. Okay. Well, I don't know. I actually think that this is hard to approximate. Even. It's not hard to solve exactly, and I'm pretty much sure that it is hard to approximate. So what people do is they try to at least approximate within a constant factor. And let me explain what that means. A common approach to hard combinatorial problems is to relax them to some problem that is tractable. So basically to replace it with some problems that's easier to solve, and hopefully that problem will give you a good approximation to the original one. Maybe relax it to a convex program or something like that. And we'll discuss two types of relaxations today. One is the spectral, and the other will be semi-definite. So spectral relaxation. Spectral relaxations. All right, so we want to maximize, again, let's, for the sake of concreteness, let's say we want to maximize this. Sum of a, I, j, just the quadratic form, xi, xj. Okay, so the main problem here, or one of the main problems, is that it is of combinatorial nature, that the set is very discrete. So the set is very discrete. It's actually a Boolean cube, something like this. So this means that x is in plus or minus 1 to the n vector. So full of plus or minus ones. It's a cube. Vertices of the cube. And the spectral relaxation is very simple. It just says, okay, let's just relax and let's replace the cube by a bigger set. What's nice bigger set? Well, a round ball, just the simplest, take the simplest shape. The circumscribed ball. So this is the cube that's inside. And this is a ball. The ball is centered, round ball is centered at 0. And let's just think, what's the radius? So what's the norm, the Euclidean length of each vector in plus or minus 1 to the n? It's the sum of plus minus 1 squared n times, then take the square root, that's root n. So the ball, the circumscribed ball has radius root n, and that's our relaxation. So the spectral relaxation, and I'll explain the word spectral in a moment, is to replace the condition that x be in the discrete cube by the condition that x lie in the round ball, the circumscribed round ball. In other words, it's the norm, the Euclidean norm be less than root n. Yeah, okay, let's see how this works. Well, obviously, because just from the fact that the ball is larger, it is obvious that the value of the maximization can only be larger. Agreed? Yeah, this is just obvious because we increased the set for which we maximize. Nothing really happened here. Okay, the root n is just a normalization factor. So I can replace root n by 1 and renormalize things. Let me think. So if we replace root n by 1, it will enter twice. So it will be the correct homogeneity is n here. So the factor will be n times the maximum over the unit vectors aij, xi, xj. So far so good. Okay, now it's kind of familiar. This is a quadratic form for sure, right? So this is x transpose ax in the linear algebra notation, or maybe you prefer something like this, the inner product between scalar product between ax and x. Either way, it's a quadratic form in A, and A is symmetric. Let's assume that A is symmetric. Say for adjacent symmetrics, it's clear. If A is symmetric, then what is it? Does this ring a bell? You have quadratic form, so x transpose ax. We have just a canonical quadratic form, and then you maximize it over unit vectors. What would that be? Does anyone know? Okay. A little hint. It's spectral, so it has to relate to either eigenvalues or eigenvectors or something like that. It's a quadratic form. So it's like ellipsoid or something like this. I don't know. The longest same axis of the no, you haven't. Okay. Okay.
It seems to be a maximum of eigenvalues.
Yeah, it's a maximum of eigenvalues. Exactly. It's one of the characterization of the eigenvalues. Yeah. If you don't know that, how can you? Is there a way to get this in 10 seconds to explain why this holds or not? This is that this thing, that thing. Maximum of x transpose ax over unit vectors x is the largest eigenvalue. So this is the largest eigenvalue of A.
I could try to explain.
Yeah, I was trying to make a, if there is a quick proof of that, like in one line or 2 lines.
Okay, so if we subtract this lambda 1 A, this can be viewed as x transpose multiplied by lambda 1 A multiplied by x, so it will be x transpose multiplied by A minus lambda 1 of A multiplied by x, and A minus lambda 1 of A is non-positive matrix.
Yeah, well, you have to know that too, right? How do you know? Yeah, that if you subtract the, yeah.
It can be easily derived if we look at further normal form.
Yeah, okay. Yeah, that way. Okay. Yeah, I guess so. So you can do that, or just as Vladislav was explaining, I thought about a similar approach where you use a spectral theorem, the spectral decomposition for self-adjoint matrices, for symmetric matrices. That should be in linear algebra. So if you have that, then it's a little example to maximize this form. So this will be sum of lambda I ui x, I guess, squared, something like that. And if you maximize that, UIs are all orthogonal. So the maximum over the orthogonal will pick up the UI with the largest lambda. And so that will be a good proof. Okay, sorry guys, I don't know how, maybe, so this is one thing that's kind of a bit of a background from linear algebra that I would love you to remember, is that if we maximize a quadratic form over unit vectors, so this here, that is a spectral quantity. So specifically, it's the largest eigenvalue of the matrix. So the moral of this story is that when we relax this problem this way, the solution becomes not trivial, but becomes easy. It's just the largest eigenvalue. And the maximizer, the x that achieves the maximum, will be the corresponding eigenvector. The vector that corresponds to the largest eigenvalue. Done, right? This can be done. You can put this in the computer. You can put it in the computer and say, diagonalize this matrix. Give me the eigenvalues, eigenvectors, and you choose the largest. Done. So this is how spectral relaxations work. We replace the feasible set, the set over which we maximize, which is very hard. In this case, it's just a Boolean cube, let's say something like that. We replace a difficult set with an easy set, and the easy is round, something that has Euclidean structure. Once we do this, it becomes spectral. So you can solve it using just MATLAB or something like that. Very easy. So this is efficiently computable. That's good. Computable. What's bad? Why is this not solving all our problems? What do you think?
Because it's a different problem slightly.
Yeah, actually, yeah, it's a different problem slightly. Yeah, we replace it with a larger set, so we get a larger maximum. Okay, and we have some solution X to that. How do we know we can go back to the original problem? Is it tight? Do we have? Well, maybe we lost everything. Maybe we lost track with reality by relaxing into the big problem. There is no way back. That's a problem. So the tightness of relaxation is not clear, is questionable. So what does it say about the original problem? Okay, we relax, and then what? So how do you know it has any connection to the original problem? We do not know that in general. In specific cases, we do know. And if you Google up, spectral relaxation of, then you will have the list of all possible things where people prove in specific situations, let's say for specific graphs, that spectral relaxations work. Graphs or some data sets. And people use spectral relaxations all the time. It's just that we have to justify it. And there is no general justification. So there is an alternative, a better alternative, because the one that does have a justification always, and that is called semidefinite. Semidefinite relaxation. That's a class, so semidefinite relaxations. Okay, so I'll explain what semidefinite means, but really it is a convex program. So we would like to relax the hard problem to a convex convex problem or convex program, where we would maximize or minimize a linear function over a convex set. This is computable always. This is an easy convex program, minimize a linear or maximize linear function over a convex set, and geometrically it corresponds to just taking the level set of this convex function, let's say something like this, and then you slide this level set until it touches that point, that direction. Okay, so there are available solvers, commercial solvers, and more specialized research solvers to solve any kind of convex program. So this is especially with the linear objective function. So that would be good if we have that. Okay, so how do we construct a convex relaxation? How do we relax this hard optimization problem to something that's convex? Aij, xi, xj. This is crazy because it fails in both respects. It's the objective function is not linear to start with. It's quadratic. It's here xi, xj. Right? It's not linear, and of course the feasible set is not convex. It's a cube. And we already decided that replacing the cube with something nice like this, the sphere is not going to work in general. So this starts like very dubious proposal, but here's how we do it. Okay, beautiful approach. First of all, how do we make this a linear function? The problem is that we have a quadratic thing there, right? Xi, xj. That's quadratic. So let's make that a variable. Xi, xj, let's make that a variable gij. Now it's linear in G. Yeah, okay. So it's linear in gij, it's just a linear form in GIJs. Okay, we got that. That's first thing. So in other words, the new variable now is not x, but it's a matrix G, which has entries xi, xj, I, and j from 1 to n. So if we solve it in G, we will get it. But the problem is that, again, the tightness is nowhere near. It's too much of a relaxation. We need a couple of things. It would be silly to maximize here over all possible metrics G, because we know something about matrix G. It's not an arbitrary matrix. It's xi, xj. So what do we know about G specifically? Let's check it out. So the matrix G has the form XX transpose. X transpose, if you multiply that together.
Looks like a gram matrix.
Daniel, can you say it again? I didn't catch that.
Looks like a gram matrix or else.
Yeah, it looks like a gram. It's not gram matrix. It's xi, it's gram matrix of vectors in one dimension, right? Yeah, but you really have a point. It looks like the metric is very specific form. It's almost like gram matrix xi, xj. So first of all, from this we know that G is symmetric. That's obvious, right? Xi, xj. You reflect it, we'll get xj, xi, which is the same thing. B, the diagonal of that matrix, GII, that's xi squared. And remember, xi is plus or minus 1, so the square kills the sign, so this is 1. So the diagonal is full of ones, like this. Symmetric matrix, 1 on the diagonal. And by the way, both of which we could enforce, right? If we can maximize over matrices with ones on the diagonal. That's fine. It's just a linear constraint. We can enforce the symmetry constraint. It's just a linear constraint, so that's fine. We can throw that in as we maximize. C is most interesting. It's a positive semi-definite. Which will denote like this, like curved greater than 0. What is the Ukrainian term for positive definite, positive semi-definite?
Додатня визначена, додатньо напіввизначена.
Додатня.
Додатньо напіввизначена.
Додатньо напів. Вау, окей. Додатньо напіввизначена, так?
Yeah.
Thank you. So додатньо напіввизначена. So G is a positive semi-definite matrix, which means, by definition, and we'll remind you that any quadratic form like this is non-negative for any U. This is easy to see for this specific matrix. Let's see. So let's make this U transpose, then G is X transpose U. So U transpose X times X transpose U. Okay. So each of these is an inner product between X and U. So we get UX squared, and that's always non-negative. Okay. Okay, so let me explain one more time the logic here. We have a difficult problem. The first place why it is difficult is that we have a quadratic form. The proposal is to make it linear trivially, automatically, just by introducing a new variable, Gij. Then it is linear. And then what? Then we maximize over all possible Gijs? Crazy. We'll get out of check with reality. We'll get much bigger maximum. So we should use some information about G. G is this matrix Gij is not an arbitrary metric. We should throw that into our constraints. And we know a lot about this matrix like this. So we can throw that in. So we can relax now. Here's a proposal. We relax this matrix, relax this problem to maximizing the Aij, Gij, linear form, perfect, we're happy here. Over all matrices G that are positive semi-definite and have ones on the diagonal. And we're claiming that this is a convex function. It's a convex program. So first of all, the objective function the function that we're trying to maximize is obviously linear in G, just the way it is, we just add here, linear in G. And the feasible set, the set over which we maximize, the set of all matrices that are positive semi-definite and have ones on the diagonal is convex. Okay, this we need a little bit to start to think about. Okay, why is it convex? It has a lot of constraints here. So one constraint is that the positive semi-definite, the restriction that G is positive, G be positive semi-definite. Is this a convex set? Like we would look at all the set of all matrices that are positive semi-definite. Is it convex? Is it obvious? This is a definition of positive semi-definite. And just remember what definition of convex is. If we have one matrix here in the set, positive semi-definite, and if we have another matrix, also positive semi-definite, then the interval joining them must also be positive semi-definite. So anything here, let's say halfway, let's just say G plus H over 2. Is it positive semi-definite? Sure. Yeah. If this holds for G, if this holds for H, then you just add G and H, divide by 2, and it also holds for G plus H over 2. Yeah. So it's almost trivial that the set is convex, that the positive semi-definite is a convex constraint. And this set is very interesting. It's called the spectrahedron. Spectrahedron. It's very hard to visualize it, because the first non-trivial positive semi-definite matrix lies in dimension 2, right? 2 by 2 is 4. So it's 4 dimension. There is no spectrahedron in dimension less than 4, and so it's really hard to visualize. But in dimension 4, you can project in dimension 3, and you could Google up Wikipedia. It's really funny set, very beautiful set. Convex. And the other constraints that we have, GII equal 1, each of them, and therefore all of them together are linear. And when you intersect linear and convex, you get convex. That's clear. You just slice a convex set, and the slice will be convex too. So I just explained why the feasible set is convex. So that means the happy conclusion is that this thing is a convex program.
May I ask?
Yeah.
About those 3 conditions on G, are those conditions guarantee that G can be decomposed into the outer product of some X and X transpose?
Oh yeah, beautiful question. Exactly. That's a great question. Do these conditions guarantee that G can be written as XX transpose? No. So XX transpose, actually, well, if you think of X here, any metric that's XX transpose has rank 1. Agreed? Because it's X has rank, it's n by 1 matrix. So it's rank 1. And of course, positive semi-definite matrices with 1 on the diagonal, there could be very high rank. Any rank actually, up to n. And so no. Now, if it was true, if it were true what you're saying, if it could be decomposed as X transpose, then it would be formally equivalent. There would not be a relaxation even. Then we would have solved the NP-hard problem directly and exactly. And we would get a Nobel Prize for that or something like that. And so, and that unfortunately is not true. Yeah.
So there's really a way how to turn the solution of this second problem into the solution in terms of X, but approximate. Yeah.
Yeah. I'm getting there. Yes, that's a great question. Yes. So unfortunately, it is not true. And so people now, if you look at the papers, many people try to impose something like this, something like a rank 1. Unfortunately, rank 1 constraint is not convex. Right? You can easily have rank 1 matrix like XX transpose, rank 1 matrix YY transpose, add them up, divide by 2, XX transpose plus YY transpose, divide by 2, and the result is not rank 1. The result is probably rank 2 for most matrices. So rank 1 constraint is not convex. It's a weird set, but it's not convex. There are ways to convexify that constraints, and people do that all the time. Just may impose some kind of a low rank restriction, relax around low rank. It's a very active area of research, and we will not do that. We'll actually do not need that at this point, because even without that constraint, even by ignoring this fact, we will still be able to get a good approximation. And yeah, so moving forward, just showing you what we will do on Friday is we will show that this problem, so formally, of course, we know that this is larger just by taking a larger set. We will show that it is a tight approximation. So here we'll have the opposite direction with an absolute constant. C times that. So this up to an absolute constant factor, and the constant is not so bad. I think it's like 2 or 3 or something like this. The best known. These problems are equivalent to each other. It is, I think it is not possible. Everyone would be happy if this constant is something like 1 plus epsilon or 1 minus epsilon, very, very close to 1. So within, but I don't think that's true. Yeah. So we will do that next time, and the result that we will show to support that is called Grothendieck's inequality, which is very beautiful. I think one of the gems in mathematics of the 20th century. So we'll prove that and then get it. Good. Any questions? Yeah, by the way, and we're doing this because it relates to probabilities. We'll prove Grothendieck's inequality and we prove other stuff using probability theory. Right now, there is nothing random here, but it will come.
So it seems that the maximum values will be connected with this constant. So we will have this relationship. But what about the vectors where we achieve?
Oh, yeah. Great question. Yeah. So yeah, so just from this, and even if we prove this inequality, even if we say that maximum of one is within like 3 times maximum of the other, great. But maybe the vectors are completely different. It doesn't approximate the vectors, right? And we will do that too. Actually, yeah, it's possible. So we, I think we will do that in one case for max cut. Specifically for the max, it's just easier to work with max cut problem, which is this. The only difference is that we have not xi xj, but 1 minus xj. It doesn't really matter, but we will do that on this specific example. We will show how to convert the solution from gij's back to xi's, which is really approximate. It's actually, it's not that hard actually to guess, but it's so beautiful. Any positive semi-definite matrix, like someone already guessed, is a gram matrix of some vectors. So we can, that's a general fact. Any positive semi-definite is a gram matrix of some set of vectors. So relaxation will give us vectors instead of signs. We just have to convert the vectors, capital Xi's, into signs, which are little xi's. And we do this by quantization, which is very harshly quantize them in a probabilistic way. We'll quantize these vectors and we get the sign. So that's how we convert back the solution. That's actually a very, very interesting result. Germans and Williams, which we'll prove. Any other questions? Perfect. Okay, guys, I will stay here. You have a very wonderful and safe weekend. Put in the calendar on Tuesday is a guest time for same time as we usually meet. Stop recording.